Welcome to Let's Get to the Marks. Going through a little quick titration question. Let's get into it. 0.1 mole per decimeter solution of sodium hydroxide was gradually added to 25 centimeter cubed of a solution of a weak acid HX in the presence of a suitable indicator. A graph was plotted of pH against the volume of sodium hydroxide solution as shown in figure 1. The first reading, or the first pH reading, was taken after 20 centimeter cubed of sodium hydroxide solution had been added. The acid dissociation constant of HX, K equals 2.62 times 10 to the minus 5 mole per decimeter. Okay, 0.1. I'm going to write some details down on the side here. Like when you scan reading this, you know you're going to do some calculations. So I'll get down that concentration, label it that that's the sodium hydroxide, 0.1 mole sodium hydroxide. Label the fact that we've been told we've got 25 centimeter cubed of weak acid or was neutralized, and that we've been given the Ka 2.62 times 10 to the minus 5. We're now told the pH range of an indicator suggests the pH range of a suitable indicator for this titration. Well, you want to look at this straight line, this vertical line here. This is known as the end point. And what we want to do there is don't look at the curves, just look at the straight bits of that. And the pH range is between 7 and 10.2, but any two values between that. You could have said 8 to 10, or you could have said 8 to 9.5 just to be safe. Make sure your values do not go on any of the curve part. Give the expression for the acid dissociation constant for HX. Ka is equal to H plus times X minus, basically over HX. So when an acid dissociates, partially dissociates to form H plus and X minus. So you're doing kind of like products over reactants, like with Kc. Don't show this one here where you do Ka is equal to H plus squared. That is true, but they've asked for the expression in terms of HX. So don't show that one. Do the first one. Okay. Let's sing down to the next part. Of course, you can pause the video and have a go. 4.3. Calculate the concentration of HX in the original solution. So we want to know, what do we have? Well, we've got the mole per decimeter. We've got the conc of NaOH, and we've got the volume of acid. But we need at least 2 out of the N over CV for one of these. So let's go for the sodium hydroxide because the graph shows you the volume. So if we find where it's been neutralized, that's anywhere on the straight line, let's draw a line down to intersect the volume of sodium hydroxide at the bottom, and we'll know how much sodium hydroxide was neutralized, was needed to be added to the 25 centimeter cubed of acid. We need 24 centimeter cubed of sodium hydroxide. We now know the volume of sodium hydroxide. They gave us the concentration at the start in the stem. Remember, I wrote down 0.10 whatever mole per decimeter NaOH. So now we know the volume and the conc. How do we work out the moles of sodium hydroxide? So you should know the equation for that. You also will need to write out an equation of NaOH plus HX so you can see what ratio they react in. Now, the fact that HX is monoprotic, it's got one hydrogen ion, we know it's going to be a one-to-one reaction with NaOH because it's just one hydroxide and one hydrogen make one molecule of water. So like this, I'm writing the equation here. So we know we're going to get NaX, which is the salt, and we're going to get H2O. So I know this reacts in a one-to-one here. So let's work out the moles of NaOH. As it's one-to-one, we'll then know the moles of the acid, and we've got the volume of the acid. So let's do the moles of the base first. 24 centimeter cubed is the volume. What do you have to do that to convert to decimeters? Remember, titrations, and in most of the chemistry, centimeter cubed is turned to decimeters when you're dealing with solutions and stuff. So we're going to do this equation here, N over C times V. I can fit it in down there. So we want to do C times V. So 0.1 is the conc of the sodium hydroxide times by 24 over 1,000. That's basically 0.024. And then we're going to get 2.4 times 10 to the minus 3. And that is the moles of sodium hydroxide. Look at our equation. How many moles of weak acid will have been neutralized? Well, it must be the same because you've got one hydrogen there that needs to go with the OH on the NaOH. So that means that we have we've got 2.4 times 10 to the minus 3 moles of HX, the weak acid. So now let's find the concentration by dividing by the volume of the weak acid, which we were given in the stem was 25 centimeter cubed, converted to dm by dividing 25 by 1,000, 2.4 times 10 to the minus 3 over 0.025. We get 0.096 mole per decimeter cubed. Bosh, that's going to get you 2 marks There you go. Lovely jubbly. Now, moving on to 4.4, remember you can pause the video if you need to, have a go on scrap paper, bust out the calculator, then unpause and watch the walkthrough. Calculate the pH of a solution of HX before the addition of sodium hydroxide. They give us a concentration to use for HX, 0.6, if we couldn't work it out for the previous question. Now, we know that the concentration of HX is 0.096 mole per decimeter. So we know HX. So write out your Ka expression again. In fact, we already wrote it earlier in the question, in one of the earlier parts of the question. So we're just going to rewrite the expression. And we know that Ka is equal to H plus times X minus divided by Hx. We want to rearrange to find H plus because the minus log of the concentration of hydrogen ions will give us the pH. So let's write this out. Ka is equal to 2.62 times 10 to the minus 5. We know that. We also know that Ka is equal to H plus, the concentration of the hydrogen ions, times concentration of X minus over the concentration of the weak acid HX, which we know because we know that's 0.096. We know that when the weak acid breaks down that H plus is equal to X minus, so we can just write H plus squared. We know that we can rearrange this now to make H plus the subject. So what we want to do is 2.62 times 10 to the minus 5, multiply that by Hx, which is 0.096 mole per dm to the minus 3. So that's Ka times Hx. That gives us H plus squared. Now we want to get rid of the square. So what we really want to do is square root both sides. And by squaring both sides, we're going to be left with the square root of 2.62 times 10 to the minus 5 times 0.096 gives us the hydrogen ion concentration. And so therefore, we're going to be left with, let's have a little look here. We got 1.59 times 10 to the minus 3. Now we want to minus log that, minus log 1.59 times 10 to the minus 3, which is the hydrogen ion concentration, and we get 2.80. That is the pH of HX at the start. And there we go, 2 marks. Right. Let's move on, get this into focus. 4.5, calculate the pH of the solution when half of the acid has reacted. You need to know this rule off by heart. If you don't know it, this is a great chance for you to lock this away into your knowledge, write it on a revision card and revise it. If you don't know it by now, the exams are coming up. So get this locked in. At half neutralization, the pH at the half neutralization point, the pH is equal to the pKa. So we can just do, if we want to find the pH when it's half neutralized, we can do minus log the Ka, because pKa is basically like pH for Ka. So we just do minus log the Ka, and we just do minus log 2.62 times 10 to the minus 5, and we don't get 7.38. That's a mistake in my calculator. Hold on. The old dodgy scientific calculator. Do not put that down. That's not the correct answer. Yeah, it's 4.58. I was going to say, if you're neutralizing a weak acid and you're only halfway there, you're not going to be at 7.38, are you? So, bit of common sense. Messed up with my calculator there. Not using brackets, always bad news. Right, where are we? 4.6. Plot your answers to questions 4.4, which was 2.80, and 4.5, which was 4.58. Plot those on the grid in figure 1. Use these points to sketch the missing part of the curve between 0 and 20 centimeter cubed of sodium hydroxide solution. So remember that we had 2.80 was at the start of the solution, the pH of the acid. So we know we're starting at 2.80. And we know that at half the neutralization point, it was 4.58. So what I'm doing, the total amount of alkali added was 24 centimeters. So I'm going to 12 centimeters and I'm putting a dot at 4.58 because obviously once we've half neutralized at 4.58. It must have been after 12 centimeters were added, which is half the volume of sodium hydroxide. I'm then making a dot at 0 because the acid right at the start had a pH of 2.80. So I've got a dot at 0 at 2.8 pH, and there we go. Don't forget, sharing's caring. Hit the like, punch up the bell, subscribe. Let's get to the marks and smash those exams. All right, people, catch you in the next vid.
You're still here? It's over.